Funding for this program is made possible by the Corporation for Public Broadcasting and contributions to this station. Coming up, what do you do with a $2 billion spaceship when it can't fly anymore?
This was a challenging project. When you look at trying to display an orbiter as if it's flying in space, we're trying to recreate that experience here on Earth.
And a Vatican observatory? It's not as crazy as it sounds.
Until the end of the 19th century, most of the people doing the day-to-day science were clergymen.
Exploring the frontiers of science. Probing cutting-edge technologies. Seeking answers to the big questions. Welcome to SciTech Central. The orbiter Atlantis flew 33 missions, deployed 14 satellites, and traveled over 125 million miles. But she didn't lose her purpose when the shuttle program ended in 2011. Her new home is just a few miles from the spot where she was launched, and she continues to inspire new generations of space enthusiasts.
3, 2, 1.
Ignition and liftoff. Liftoff of Atlantis. A new orbiter joins the shuttle fleet, and it has cleared the tower.
The space shuttle is probably the most marvelous flying machine that man has ever built. Not only could it carry astronauts to and from space, but it could carry a very large amount of cargo as well.
John Creighton flew 3 shuttle missions, but one holds a special place for him.
Atlantis is near and dear to my heart because that was the vehicle that I flew the first time as the commander on the space shuttle.
135 missions. 2,000 tons, 2.5 million moving parts. The orbiter vehicles, as they were officially known, were the largest, most expensive, and most complex spacecraft ever built. But like everything, they had a finite lifespan.
When the shuttle program was going to conclude, NASA took a look at what to do with the remaining 3 orbiters from the program and made the decision that each would be displayed in museums throughout the country.
On the 30th anniversary of the first shuttle flight, NASA announced which facilities would receive the orbiters.
We were thrilled to find out that Space Shuttle Atlantis was going to be here at Kennedy Space Center Visitor Complex.
Then, the real work began.
We looked at this Space Shuttle exhibit as the cornerstone and wanted to do something dramatic and showcase the orbiter as no other place on the planet. This was a challenging project. When you look at trying to display an orbiter as if it's flying in space, we're trying to recreate that experience here on Earth.
Construction on the new exhibit building began in January 2012. Meanwhile, Atlantis was being prepped for her new role.
To fuel the space shuttle, you have liquid hydrogen, liquid oxygen, and residues from those fuels can be left in the engines. So a lot of time and a lot of care went into making sure that those chemicals removed so that we can provide a safe viewing environment for the guests.
Next, Atlantis had to be transported to the visitor complex.
We moved 123 light poles, 23 traffic signs, 56 traffic signals. It was a 10-mile journey in all, something that took nearly a day. We constructed the Atlantis building, but left the north wall open so that Atlantis could slide right in. How do you carefully lift this orbiter? You have one shot at that. You don't want anything to go awry because you've got a $2 billion artifact that can't be recreated. We had to install steel beams, 60 feet long, carefully lifted the shuttle, beginning at 2-inch increments for several days. While that was happening, Atlantis was being shrink-wrapped to surround and protect her. Several months later, when we unwrapped Atlantis and needed to open the payload bay doors, we brought in a special brace that we put on the edges of the payload bay doors, carefully opened them, and then using 6 long cables of steel, we're able to secure the payload bay doors in an open position.
For many of those visiting the exhibit, Atlantis is as inspiring in repose as she was in flight.
I think it takes your breath away.
From TV, all you see is this smooth white, what you think is this perfectly clean, unused vehicle, but it's got so much more history to it.
You see everything, you just think, whoa, that's amazing.
A breathtaking experience, magnificent, outstanding. I never thought I would see a real spaceship up close, like standing right in front of it right there.
I think we're so used to seeing things on television and it doesn't necessarily feel real, but when you come and see it in person, it's huge, it's impressive, and you really get a better feel of what it was like.
The visitor center here has done an amazing job of displaying Atlantis. Far and away, the best of the other orbiters that are, now on display at museums around the United States.
The Space Shuttle Atlantis attraction has exceeded our expectations. Millions of people have seen this from around the world.
Atlantis made history as a flying machine and now makes a unique museum piece. But her most important role may lie in the future.
We need to get more people interested in the technical areas. You see kids come around here and they have an opportunity to talk to them, and they're all excited about that. We need that kind of technical talent. Public has an opportunity to go around and learn not only about what we did with the space shuttle, but why we go into space and what's coming in the future.
Control, this is Commander.
Our purpose here at Camp Kennedy Space Center is to inspire young children and just getting them excited that we still have a very large presence up there in space.
Start up successfully.
My favorite part of the camp was probably some of the simulators that we did. We did one where it was called the gravity wall, and you felt like you were weightless. It was really cool and unlike anything I'd ever done before.
You're weightless.
We have a Slingshot to Mars activity where they take a raw astronaut and we launch it to see if they can build a capsule to support their astronaut.
Giant egg survived!
It was awesome. My egg actually survived, and I slingshot it with 2-stage fuel.
They create a fun learning environment without them realizing that they're really learning a lot.
I really see what it's like to work with a team. Parts of it were hard and parts of it were fun because of the contrasting ideas that we had. But then once we all came together, it was really fun.
These are going to be our future rocket engineers, our rocket scientists, our astronauts, and it's a good place to start right here at Camp KSC.
The Google Lunar X Prize competition pits 16 teams in a race to the moon, with $30 million in prizes at stake. Team part-time scientists recently spent time at a simulated lunar surface in Bremen, Germany, to test one of their instruments.
I'm Andrew Barton. I'm the Technical Operations Director for the Google Lunar X Prize. I'm here today at DFKI in Bremen, Germany, with one of the judges from the Google Lunar X Prize. We're here to look at some testing activities being done by the team part-time scientists. They're a bunch of guys who are technically active in other industries, and they've got together to form a team to go after the Google Lunar X Prize in their spare time.
The team formed about 4 years ago when I first heard about the Google Lunar X Prize. From there on it really just grew the entire team, and yeah, it's been 4 years since.
I'm Alan Wells. I'm an emeritus professor at the University of Leicester, and I'm one of the Google X Prize judges. Google have introduced these milestone prizes as a stimulus and as a means of measuring genuine progress towards the ultimate objective. And that's where we are at the moment.
The goal of the test here today is to verify the image quality of the camera. So the reason why we've come here to the DFKI Institute is because they have this very awesome space hall, which is capable of simulating realistic lunar lighting conditions.
To demonstrate sort of very high resolution and high frame rate video is something that is not that easy to do.
The thing that we want to achieve today is actually verify that the image quality of the camera that we have built, this latest prototype, matches up with the requirements of the MTA. MTA is the Master Team Agreement, basically the rules of the competition. So if it doesn't match up and we send it to space, then we can actually get disqualified. The reason why you saw us putting up different filters in front of the camera is actually because we're mixing two different types of cameras. So we're having two black and white cameras, which are the parallel ones. They were the ones for the stereoscopic imaging that we use to do this 3D scanning of the surface and measuring distances to certain focal points. And then we have, of course, the telelens, which is in the middle. And the telelens is actually different in a way that the other two cameras actually already color sensors, so they're capable of seeing color themselves. But the telelens is a black and white sensor. If you use a color sensor to capture your colored image, that's totally fine, but the point is the quality is better if you use a black and white sensor and apply the right kinds of filters. What we did to be able to get things done quickly and tested quickly is that we've ordered all of the parts from the camera as 3D printed parts, so they're basically plastic. This gave us the advantage that we could quickly test the image quality. But of course it has the disadvantage that we can't do all of the other tests that we want to do. For example, the thermal vacuum test is something that you can't do with the plastic parts, or the mechanical load test. But of course for the image quality it doesn't matter if the housing is plastic. The reason why I believe this entire Google Lunar X Prize and part-time scientists is pretty awesome, at least for me and for most of the people on our team, is that you get to learn so much more things that you would have never come in contact with in your normal life. I think if we win the GLX3, we're already full time.
Hi, my name's Tyler Losokowski. I'm an aerospace engineer here at the Flight Dynamics facility. Today you're going to see my typical day starting around 9 a.m. I start my day by checking my email, and then I look at my calendar to see what's on the agenda for the day. So in the morning we're going to start with monitoring the status of daily ops. So right now we're going to be looking at the status of daily ops. So daily ops consists of a number of different satellites, and in this case it looks like all of the processes have passed and there is no need for any manual intervention by the analyst. Now it's time to head to the analysis meeting. We have this meeting once a week. In the meeting we discuss ongoing analysis projects in the FDF. We discuss ways to improve them or possible new projects that we could be working on. If we had.
We did a lot of use cases.
Now we're going to send an update to the International Space Station to tell it where to point at the TDRS satellites. This will allow the International Space Station to point their antenna at the TDRS. This way they can communicate with the Earth at all times. Now we're going to head to a slide review for a conference we're going to be having with White Sands Complex, New Mexico employees. What the batch process is, define daily production, or if we use this delta V image. Now that the review is over, I have to take those comments and incorporate them back into my slides. Once that's done, it's quitting time, and I get to go play soccer at the Goddard Soccer League. It's a typical day in the life of an aerospace engineer.
Sometime in the next decade or so, the world-famous Hubble Space Telescope will fail. John Morse, a former NASA scientist, is proposing a new telescope that would continue some of the groundbreaking work of the Hubble.
Astro 1 is a space telescope that is meant for the era beyond the Hubble Space Telescope. Hubble has probably a finite lifetime towards the end of this decade or so before its capabilities will be severely degraded.
Yes, that's right. The world-famous Hubble Space Telescope will likely be retired sometime around 2020, leaving a hole, so to speak, in our intergalactic field of view. To fix this, NASA veteran John Morse started Boldly Go, and he's hoping to build a new telescope that can continue to capture the spectrum of light that Hubble did.
Right now, in NASA's missions that they're planning, there's no capability for ultraviolet spectroscopy, which is one of the mainstays of space astronomy.
This new telescope, tentatively titled Astro 1, will be a lighter and smaller version of its cousin the Hubble. Like its predecessor, Astro 1 will capture ultraviolet light images, but it'll have a 10 times larger field of view thanks to updated technology from the same company that helped build Hubble.
New York's own Corning Incorporated recently made a major donation to Boldly Go to create a new space telescope mirror, similar to this prototype that was created for the famous Hubble telescope.
So if you can envision a honeycomb, so it's mostly air,
but it's very strong still. So that's essentially what we're making is a honeycomb structure out of low expansion material, which is our ULE, to make the primary mirror. And it will be very rigid and allow the telescope to focus very precisely.
Nestled in the northern town of Canton, just outside the Adirondack State Park, is one of Corning Glass's high-tech facilities. In 1978, the company built the glass mirrors for the Hubble telescope that were lightweighted by 60%, meaning for a glass structure its size, they were able to reduce the weight by 60%. With today's technology, they can produce the same piece that's lightweighted by 90% while maintaining the same structural integrity.
When the temperature changes, essentially the mirror structure does not change. It stays very constant, which again allows you to focus very precisely over a large temperature gradient.
This may seem like a minor detail, but it's crucial for space telescopes. Outside of the Earth's atmosphere, temperatures can swing as much as 300 degrees in a matter of seconds, and telescope glass simply cannot afford to crack.
Once the Corning glass components are finished in Canton, they'll be sent here to Excelis in Rochester, New York, where they'll be polished and finished and fitted for the Astro 1 telescope.
We can produce very clear images from space. As a matter of fact, we've produced 99% of all the optics that take pictures from space, both looking at the Earth and looking out into space.
Excelis has 50 years of experience building space telescopes, like this prototype of a satellite built for Digital Globe earlier this year. Once they receive the light-weighted glass components from Canton, they'll be coated with a light reflective material like aluminum and then mounted into the middle of the telescope as its primary mirror. Excelis will then produce a secondary mirror that will sit behind the primary mirror and transfer collected light onto an instrument screen. The mirrors will be held in place with a highly stable composite, keeping the entire structure as light as possible.
The benefit for that is the spacecraft can then put that lower mass or that lower weight farther into space. And it also allows the mission to last longer because not as much fuel is required to maneuver it once it's in place.
Once completed, Astro 1 will be sent 1 million miles into space to collect images like dark matter. The ultraviolet light it collects will help determine how fast an object is moving, what it's made of, and determine its temperature and density.
We will also be able to investigate exoplanets around nearby stars. Our off-axis design is what people have been talking about for at least 15 years about what is needed to make really clean stellar images.
Morse says Astro 1 will actually help the astronomical community take on space frontier projects with private funding. The Astro 1 telescope wouldn't take the place but simply build on the legacy of Hubble. But despite Corning's $1.8 million glass donation and private fundraising, the telescope project isn't anywhere near completion. Morse says the entire Astro 1 project will likely cost $500 million and won't get off the ground until 2025 at the earliest.
In 2006, NASA launched the New Horizons spacecraft to study Pluto, its moons, and the Kuiper Belt. We recently sat down with Dr. Alan Stern, the mission's principal investigator, to learn a little more about this historic undertaking.
New Horizons is NASA's exploration mission to the Pluto system and the Kuiper Belt. It turns out that the understanding of the Kuiper Belt is important to understanding the formation of the solar system because the Kuiper Belt is kind of the solar system's attic. It's where all of the ancient objects, the building blocks of the planets, and this new class of small planets is located. And we didn't know about it until the 1990s. We used to think of the solar system as the 4 inner rocky planets and then the 4 giant planets. We thought the giant planets were the outer solar system. They're really the middle solar system. This is the whole 3rd region. From the data sets that we'll collect with New Horizons, we're going to learn a great deal about the Pluto system and how it came to be. And that's going to help us connect the dots for how the planets formed. We're learning that the Earth and the planets like the Earth are actually the oddballs, that there are a lot more small planets than there are big planets. But even these objects are not that small. If you were to drive around Pluto's equator and clock the distance, it's as far as from Manhattan to Moscow. The consensus today is that Pluto as a dwarf planet is a type of planet. Just like the Sun, if you look it up in a textbook, is called a dwarf star. Doesn't make it not a star.
Brother Guy Consolmagno is the 2014 Carl Sagan Prize winner, a popular science writer, an astronomer, and a Vatican official. On a recent trip to the U.S., he shared some of his views on science, religion, and the perfect job.
I'm Brother Guy Consolmagno. I'm the president of the Vatican Observatory Foundation, which is the foundation that raises money to support the Vatican Observatory's telescope in Arizona. I'm also a scientist. I use that telescope. I observe asteroids and Kuiper Belt objects, those things out beyond Pluto. And in addition to that, my real background is in the geology of planets, so I study the meteorites, the rocks that come from the asteroids, and maybe we'll get pieces someday from the Kuiper Belt. So my whole work is trying to figure out how these little pieces, the pieces of junk left over from the formation of the planets, what that can tell us about how the planets were formed 4.5 billion years ago. I was in kindergarten when Sputnik was launched. I was starting my senior year of high school when people landed on the moon. But the real kick was in between those two times, you know, when all little boys were going to be scientists, and it was only boys in those days, I'm afraid. But I was also fascinated by science fiction. My best friend was going to MIT. I visited him there and discovered that they had the world's largest collection of science fiction. I thought, I've got to come here, I've got to find some excuse. I saw among the list of majors, if you transferred in, Earth and planetary science, and I thought, planets, I've always liked looking at the stars. I checked that out. When I arrived, I discovered that I had signed up for the geology department. Geology? What could be more boring than, you know, there's a rock, yeah, there's another rock, yeah, what am I going to do with it? And then I discovered that there are rocks that fall out of the sky that come to us from the asteroid belt, some of them from the moon, some of them chipped off Mars. And I discovered that you could study these samples of outer space. I got so enthusiastic about the thought that I could be holding a piece of outer space. I never looked back. I became a Jesuit when I was nearly 40 years old, with the idea of teaching at a Jesuit university. But of course, you take these three vows: poverty, chastity, obedience. Poverty, I was used to, I'd been a graduate student. Chastity, I was used to, I'd been a graduate student. Obedience, I was not used to. They get to decide the work you're going to do. Before I had any chance to say, I want to teach here or I want to teach there, they came to me and said, you've been assigned to the Vatican Observatory. Under obedience, I had to go to Rome, live in this horrible palace, look at that boring scenery, eat that terrible food, and oh yes, work in a laboratory with 1,000 meteorites doing the work I'd always wanted to do. You know, it's tough, but I had taken the promise that I had to obey. People don't understand how science actually comes out of our religion. And the greatest emblem of that is the fact that until the end of the 19th century, most of the people doing the day-to-day science were clergymen. I mean, in the little village, who else has the education and the free time to go out and gather specimens? Plus, what does a clergyman do for most of their life? If they're running a parish, they're keeping track of births, deaths. It's clerical work. That's why they call it clerical. But that's exactly the same skills you need when you're a scientist, to know how to gather data and organize data. An awful lot of the science we do has in its roots the techniques that come out of theology or the techniques of just basic record keeping that you would get in the parish. The American Astronomical Society actually gave me the Carl Sagan Medal, which I am carrying around in my pocket so I can show to everybody I know. Carl Sagan was famous not just because he was a popularizer of astronomy, but he was the first. Before then, the idea was scientists are going to be serious and studious. And he said, no, this is amazing stuff we're doing. We're exploring the planets for the first time. We will be the generation who will be the first to see the surface of Mars, the surface of Venus, what the rings of Saturn really look like. And we should be excited about that.
That's all for now on SciTech Central. Thanks for watching. Join us next week for more stories from the frontiers of science and technology. Funding for this program is made possible by the Corporation for Public Broadcasting and contributions to this station.